the channel. In today's video, we are going to be discussing mathematical induction. The induction process in mathematics is a process that we use to test for the validity or trueness of a particular mathematical axiom or proposition or statement. So if a mathematical statement is true, we always try to prove using induction that it should be true for a number of variables. So if it is true for those number of variables, then we slot in other integers and to prove that this statement is valid. That is basically the process. And we do that in two stages. We have the base case. Is in the base case that we plug in different variables, known variables like 1. We usually start with 1, 1, 2, 3, as much as you want to test that it is true for those values. Then the next step is the induction step. The induction step. It is the induction step that you now test for a particular algebra that is not even given. So then if it is true for this, then you have proven that the statement or mathematical axiom is true. All right, let's take a question. The first question says, prove that 5 raised to the power n minus 1 is divisible by 4 for all positive integers of n, integer values of n. Alright, so this is a very simple question. Now, how do we attempt this question? We start with the base case. In the base case, what we basically do is we will slot in the first value that you want to test for. For example, we usually test for when n equals 1. So let's see if this statement is actually valid when n is equal to 1. So if n is equal to 1, we're going to have 5 to the power of 1 minus 1. And this becomes 5 minus 1, which is what? 4. So is this divisible by 4? Yes, it is divisible by 4. And how do you prove that? It will be 4 into bracket 1. So it is divisible by 4. Alright? Equal to so this, then we'll now say that it is true. So having proven the first base case, we'll say it is what? True for this. We can go further to test for when n equals 2. Let's test if it's true, because it's possible to be true for 1 and not be true for 2. Alright, so we have 5 raised to the power 2 now minus 1. So that we have 5 raised to the power 2 is 5 raised to the power 2 is 25 minus 1, and that becomes what? 24. Now is 24 divisible by 4? Yes, because it is 4 into bracket 6 that gives us 24. So we say it is also what? It is also true. Alright, so since we have proven for 2, you can go further to proving for 3, but at this level, I think it is true for all positive integers. And how do we now test that? Actually, in induction. So this is the induction step now. In induction, what we do is we are going to now say, we assume that the statement, assume it is true for n equals a particular algebra k. So we assume that it is true for n equals k, so that our axiom, our statement becomes 5 to the k minus 1. Alright? So we now, having changed our statement to this, we will now prove that, let's prove that it is true for n equals k plus 1. That is, every successive level of increase for k. Let's prove that it is true for it. Okay, so the proof is this. Since we have assumed here that it is true for n, this is what we do. We will now say that since we assume it is true for n, means that this thing should be divisible by 4. So it should be 4 into bracket a particular number n. Let me repeat that. We assume that it is true for n. So if it is true, it should give us this 4. That 4 will be divisible by 4 times a particular number to give us that answer. 4 times a particular number to give us that answer. So if this is actually divisible by 4, then this one should have 4 times a particular number. How that is clear. So we leave it like this. So one thing that we should now do from here is to now bring this value, this number here, so that we have 5k, make 5 raised to the power k rather, to be equal to 4n plus 1. So this becomes like our equation 1. Alright? Now the essence of doing this is for substitution's sake, and you're going to understand it very soon. So we want to now prove for k plus 1. How do we prove for k plus 1? Remember that our statement is 5 raised to the power n, so our n is now k plus 1. So we have 5 raised to the power k plus 1 minus 1. Alright? So this becomes, remember that this value in indices, we have this thing means 5 raised to the power k times, remember that if it's a raised to the power n times a, it gives us what? A raised to the power n plus 1. So you see this 1, the 1 here appears here. Alright, so it's the same case here. So it means that this thing came from 5 raised to the power k times 5. Alright, minus 1. Alright, so since we have this, now we know that 5 raised to the power k has been turned into this. So what do? Let's slot in that value here. Now that becomes what? 5 raised to the power k is now 4n. So recall that 5 raised to the power k is equal to 4n plus 1. So that we'll have 5 raised to the power k comes here, we have 4n plus 1, close bracket, we have the 5 which is multiplying it, then minus 1. Alright? Further down, we have 4 times this, 4 with 5, we open the bracket. So that we have 20n plus 5 minus 1. And then we have 20n plus 4. Alright. Now in order to be sure that this thing is actually divisible by 4, let's see. It means we are going to factor out 4. If 4 can be factored out, then it means that this axiom is actually true for even n equal to k plus 1. So 4 into bracket, here we have 5n left plus 1 left. So since 4 can be factored out, we know that it is true. So this statement, we have gotten a particular 4 in bracket L. So we are changing the form where L is this a positive integer, where L is a positive integer. So we can now further say that hence, by mathematical induction, it is proven to be true. Alright, so you can just end it up here, but actually sometimes you just like to add statement. Hence, it is true by principle of mathematical induction. Alright, so let's do one more. This is proving divisibility or factor. So let's do one more question. The second question says that we should prove, it's almost like this, is that we should prove that that 7 raised by 2n plus 1 minus 1 is, plus 1 again, is divisible by 8. Is divisible by 8. Or that 8 is a factor of this. That's what it says we should prove. Alright, so this is question 2. Now, how do we prove this? We start from the base case as well. Now, the base case is necessary because if the statement is not true for the base case, then you have no further proving to do. But if it's true for the base case, then we can go further to proving it. Alright, so how do we do the base case? We say we always start with 1, we start with 1, and then if we take that into the equation, we have 7 into bracket, 7 raised to the power 2 into bracket 1 plus 1 all plus 1. So that we have 7, 2 by 1, 2 plus 1, that is 3, then plus 1. And then this becomes 7 raised to the power 3, that's 49, 49 by 7, 3, 6, that will be 3, 4, 3 plus 1. Alright, that becomes 3, 4, 4. So let's see, is this a multiple of, is this divisible by 8? Let's try to factor out 8 here. If we factor out 8 here, we have 8 here 4 and 3. Alright? So since we can factor out this, we'll say that it is true. Alright? We can go further to test for when n equals 2. When n equals 2, we're going to have 7 to bracket 2, 7 raised to the power 2 to bracket 2 plus 1, all plus 1. So we have 7 raised to the power, this by this 4 plus 1, 5 plus 1. So 7 to the power of 5 is going to be 343, which was to the power of 3 then by 3. Okay, I think I have a calculator there too. So it gives us 16807 plus 1. This becomes 16808. Alright, so let's see if this is divisible by 8. We're going to have, we'll factor out 8, we're going to have 2101. Alright, so it is actually divisible by 8. So we can go further to prove by the induction process. So we have the induction step now. Now in the induction step, what we will do is we are going to test, assume it is true, assume that statement is true for n equals a particular k. Alright, so our statement changes to 7 to the power of 2 into bracket k plus 1 all plus 1. So that we have 7 into bracket raised to the power 2k plus 1 all plus 1. So if this is true, then it should give us a particular 8 times n in this form. Where n, you can continue by saying where n is a positive integer. Alright, so if this is true, if this is actually true by our assumption, then it means that 7 raised to the power 2k, 7 raised to the power 2k times 7 plus 1 is equal to 8n. So that 8n becomes 7 raised to the power 2k dot 7 equals 8n minus 1. Just the same way we did the other case when we brought that forward. So here we can leave it at 7 raised to the power 2k plus 1 equals 8n minus 1, right? So we can now test for when n equals prove that it is true, prove it is true. For n equals k plus 1. So this is the proof. Alright. So since we are saying it is true for n equals k plus 1, we are going to repeat the statement because 7 raised to the power 2 into bracket k now plus 1. Then plus 1, all plus 1. So that we have 7 raised to the power 2k plus 2 plus 1, all plus 1. Alright. So we know that all of this mean 7 raised to the power 2k. We can bring out 7 raised to the power 2k from there, or let's bring 7 raised to the power 2k. Let's bring this plus 1 forward. So we have plus 1 and plus 2. So that all plus 1. So that we have 7 raised to the power 2k plus 1. Remember that this 7 raised to the power 2k plus 1 times 7 squared. How this is clear? Because it's squared here. Of course, we could have brought 7 raised to the power 3 here, but we want it to resemble this equation here. So we can do this and now substitute this. So recall that 7 to 2k plus 1 to the 1 plus is equal to 8n minus 1. Alright, so we now bring that into the expression so that we have 7 squared open bracket 8n minus 1 is equal, plus 1. Alright, so is equal to 49 into bracket 8n minus 1 plus 1. So this becomes 49 by 8 gives us 392 m plus 49 minus 49 this by this, then plus 1. So that we have 392m minus 48. Alright, so let's factor out 8 if it is possible, so that, to prove that it is actually divisible by 8. So if we factor out 8 from here, we are going to have 49. 49n minus, we factor out 8 from here, it is possible, we have 6. Alright, so, and these are imitated the form 8l, where l is also a positive integer. Alright, so we can now say that hence, by principle of mathematical induction, or by simply mathematical induction, it is true. Alright, so let's solve one more question, which is not on divisibility. We are going to prove one more statement which is not on divisibility. Alright, this question says that we should show that the sum of the first n natural numbers is given by this formula. Alright, so how do we do that? Solution. So we take the base case. In the base case, we test for when n equals 1. Now this is very simple. It's just the sum that we always test for. So meaning that every operation that we do, every step we take, we make sure it is the sum of natural numbers, the sum of our items. Okay, so we are taking the base case, we are taking n equals 1. So we are taking only 1 because 1, there is nothing that is added plus 1 here. Alright, so when n equals 1, we have that 1 should be equal to 1 into bracket 1 plus 1. We are substituting every n for 1. Then by 1 rather, 1 over 2. So left hand side is 1 1. And then the right hand side should be 1 into bracket 1 plus 1 2. So that will be 1 plus 2 over 2, which is equal to 1. So right hand side, left hand side is equal to the right hand side. That's what we are after here. So it is true. The same way we used the other time. It is true. Okay? Now, when n, let's test for that. When n equals 2. So since n is now equal to, it should be the sum of the first item before 2 and 2 itself that will give us that will balance both sides, because it is the sum that is equal to that formula. Alright, so it means that it should be 1 plus 2 will be equal to, since our n is now 2 into brackets 2 plus 1 all over 2. 2 can take care of 2. So we have 1 plus 2, that's 3 equals 2 plus 1, that's 3. So right hand side is equal to left hand side. It is true. Alright. So let's now use induction. So by induction, in the induction process, we assume it is true for n equals k. So if we are assuming that it is true for n equals k, it means that our statement has turned to 1 plus 2 plus 3 plus ... plus k will be equal to k into bracket k plus 1 all over 2. Why? Because we are testing for k. So we change all n to k and our statement has also changed. So we'll now prove. Let's prove for n equals k plus 1. The same way we do as other times. So it means that what it is saying is that the first item is going to be k plus the next item is going to be k plus 1. Alright, is equal to k plus 1, which is n, open bracket, k plus 1, which is the second n, then plus 1, close bracket, all over 2. Alright, so that we have k plus 1 will be equal to k plus 1. So if this is the left hand side is giving us 2k plus 1. So let's hold the left hand side. Let's make sure the right hand side, let's try to make the right hand side equal to the left hand side. So that we have k plus 1 open bracket k plus 2 all over 2. Alright, so that we have, now remember that, no, before we do that, what we are going to do is, remember that k actually gave us this. Alright, so we'll now substitute. Recall that k is equal to k into bracket k plus 1 all over 2. So we'll substitute that here so that our left hand side, so in fact we are going to be holding the right hand side. So this is what we got for right hand side. So right hand side is equal to k plus 1 and k plus 2 all over 2. Alright, so we want to make sure that this left hand side is equal to the right hand side. So this k is now this, so we substitute it here. We have k into bracket k plus 1 all over 2, open bracket k plus 1. So what we can do is multiply through by, so in order to make the left hand side equal to the right hand side, what we'll do is, since we know that k is equal to this guy from here, we know that k is this, so we substitute it here and bring it as k into bracket k plus 1 all over 2, then plus k plus 1, right? So k can open the bracket here and we'll bring 2 here so that we have k squared plus k, then plus 2 into bracket k plus 1 so that we have all over 2. And this becomes k squared plus k plus 2k plus 2. Alright? So that we have all over 2. Then we'll have k squared. So this is going to become a quadratic expression, so that we have k squared plus 3k plus 2 all over 2. And we know that this is going to have 2 roots, which are k plus, that is going to be 3 plus 2 and plus 1. Alright, so that we have k squared plus 3 plus 2k. So we're going to use this to substitute for that. 2k plus 1k, which is k, plus, okay, exactly what we had here, plus 2. So what we simply do is now we factorize. So from where we can factor k out, we have k is still left here plus 2, and we have here k plus 2 still. Okay, so that we have 1. Alright, if 1 opens this bracket, it's going to give us this back, so that we have k plus 2, close bracket, is common between k plus 1 and k plus 1. Alright, so this becomes it over 2. Now you see that left is our left hand side now. We have made it equal to our right hand side. So we can now say that by principle of mathematical induction, it is true. Alright, so that is the end of the video. I quickly actually use this question to solve them because I received the questions from one of my persons who needed the solving. So please do also subscribe to the channel. I'm going to also release further videos on principle of mathematical induction where we'll solve more complex questions. Thank you very much.